All right, we're back. Okay, so I did make a recording over the weekend and I did post it in YouTube. Remember, yeah, the Blackboard right now for some reason is not letting me store videos, which has never been a problem in the past, but we don't ask questions about IT, I guess. So just a reminder, if you go back to my account, Dr. ACA actually, you'll see it in my playlists. We are, of course, Econ2142 Summer 2026. And so here they are. Oops, that's the one. Yes, okay, that's the one I made the other day. Oops. Anyway, so the bottom line is during that recording, I finished up chapter 11 and I did the three spreadsheets, but since we weren't live, I think I'd like to go back and revisit those three spreadsheets so you can work on them tonight. And then we can start chapter 12. Okay, so I'm going to go open up the spreadsheets, which are in Blackboard, of course, and we'll just go back and revisit them. There's three of them, and one of them does require the data analysis tool pack, which I think last time I remember somebody had an issue downloading it. Um, I don't know if that was ever resolved or not. Um, So if there's still continuing issues, you can let me know. But of course, I won't hold anyone responsible for not being able to get their hands on the data analysis tool pack. Theoretically, it should be a simple matter of downloading it, but you never know with technology. You can never count on it. That's for sure. Always have a plan B. That's for sure. But anyway, hold on. And so in chapter 11, we were introduced to both the chi-square and the F distributions because we're dealing with variances. First, we did some confidence intervals with a single variance, and then we also looked at what to do to test hypotheses about a single variance and then with two variances. And so with the single variance, or with a confidence interval about the variance, we can use the chi-square distribution. If we have two population variances, then we have to switch to the F distribution. Okay, so let me go back into Blackboard, get everything open. Now we're going to keep using these distributions. They're not going to disappear on us, especially in chapter 12. If I'm remembering correctly, it's entirely based on the chi-square distribution. There's several interesting applications that we can use it with. Um, in fact, well, there's more, but we're going to see just three of them. Also, I do want to mention that I did actually write the first midterm. Now, all the tests, as you know, are going to be on MindTap, but I need to be careful about how I set it up because if I'm not careful and I just stick it in there with the rest, it'll affect the way your averages are calculating. So I've got an email out to Cengage to ask them how I can properly post that midterm without interfering with the other grades. So when they get back to me, I'll have it posted on there. And so because this is such a short semester, my plan is to have all the exams due the last day of class, basically, because I mean, you can do them earlier. You can do everything earlier. Everything is already open, but I want to make sure that nobody has difficulty finishing because, again, of the tight schedule. There's a lot of assignments, and so you'll have a lot of flexibility with the exams. If you have some issue that, like, for example, your job suddenly sends you away to a foreign country or things like that, anything that makes it basically impossible to finish the course, you can let me know and we can request an incomplete for you. But that usually requires a fairly significant reason. But so we'll see what we can do. Okay. But if you do get an incomplete, it'll give you several weeks to finish up everything. And then that way you can still get a good grade. All right. Anyway, so let's get back to 11 now. For 11, we don't really need 11 itself. We need the spreadsheets, which were detergent with annotations, And you can see everything's waiting for us to fill in the details. So we'll get that open. Then we'll have bus times with annotation. That word, I put it in there because I had to type in all the titles. It didn't come like this from the publisher. And then we had one more, which was school bus. Okay. And this is the one where we're comparing the buses from the two different cities. Okay. Now, we'll go into 11 and remind ourselves what we were supposed to do. Let me open this up. Let's get these open. And then we can get started. Now, you may have already done this. If you watch the video, it's possible that you've already finished these and handed them in, and that's great. But I just want to make sure we're all together when I go over this part. All right, so here's the chapter. Let's see. All right, so we'll do them in the same order as the slides. So we have, and again, we started out with the interval estimation and hypothesis testing with a single variance, which required the use of the chi-square distribution. We went through the properties of the chi-square distribution. We saw how to interpret the table. Remember, the calculator doesn't have everything we need to calculate chi-square probabilities. So what we have to do is use the old-fashioned approach of the table, which is here. Let me get that open. And the important thing here is to remember that unlike what we saw in previous chapters, here we're always looking at the right tail. So whatever numbers we're looking at, like for example, the alpha or alpha over 2 in a hypothesis test, in chapter 10 and 9, we always looked in the left tail with the normal and the t. Here it's always the right tail. Okay, now luckily it does say that on the actual chart or table to remind you, but just let's be careful, okay? The other thing that's different is that because we don't have symmetry here and we don't have any negatives, we will, if there's two critical values, we'll have to look them both up separately because they're not going to be equal to the negatives of each other, which was what we found with the normal and the t. But you'll get used to it pretty quickly. So the degrees of freedom are over here, and the right tail areas are over here. So the ones you're seeing over here on the left are in the far extreme left part of the distribution. These are the ones on the right. Okay. All right, so let's get back to the slides real fast. And so we have our confidence intervals for the variance, and then you can take the square roots to get the standard deviation. And so we did some of that. Here we go, liquid detergent. Okay. So what we're going to do here is actually construct the confidence interval for the the variance of the contents of these liquid detergent bottles. And the idea here is that if the variance is too high, then we have to change the process for filling these bottles because that means that the amounts are inconsistent with each other. And we don't want that. Ideally, they'd all be the same, which means the variance would be zero, but we can't have that, expect that either. So here's the details they gave us. Actually, since we're doing the spreadsheets, the data is already here. And in fact, we're going to be asked, what happened? I don't see it. Second, it looks like the detergent didn't open up. There it is. All right, here it is. Okay, this is it. So we really don't even need to look in the slides when you think about it, but they do have to tell us what level of significance they're after. So the sample size, of course, you're going to ask for um, count. Let me just make this a little bigger. Count is the command we use for numerical values, and you just tell it where they're found. So we come over here and we select the entire column, A2 through A21. And then the variance, which means, of course, the sample variance, var.s is how Excel spells that. Then again, you're telling it that the data is in A2 through A21. And yeah, I did mention that in the slides. The confidence coefficient, if I remember correctly, was 5%, but let's confirm that. Yeah. Oh, okay. So because they want a 95% confidence, the confidence coefficient is 0.95 then, which means 95% confidence, but then the level of significance is one minus that. That's our alpha. Okay. Now, this is where it gets challenging. Chi-square lower and upper tail. What do they mean by that? Well, let's find out. Let me draw a little picture here. This is where the table comes in, but the Excel can look these up for us too. What is today? The 13th? Okay, great. It's a little bigger. Okay, and last thing I'm going to put in the pages. Yeah, if I don't go through all of this, the problem is that with the handwriting on the tablet, it'll only allow me to go one page and then that's it. So I have to take care of it. Um, One last thing, I have to save this before I lose it, and then we're good. All right, finally we're ready. Okay, so because this is chi-square, we don't have symmetry. So our job of finding critical values is a little bit more challenging. All right, let me draw this properly. All right, so the chi-square, it depends on how many degrees of freedom there are, of course, but it looks something like this. So if we have two critical values, they're going to look like this. So first of all, remember everything is in the right tail. So alpha is cut in half. Now this left tail area is also alpha over 2, but we don't label it like that. We're looking the right tail. So therefore, it's going to be 1 minus alpha over 2, because that means everything to the right of that is 1 minus alpha over 2. Now, here they gave us a 5% alpha, and the sample size was 20. That's important because that tells us how many degrees of freedom there are, which we need to look up values in this chi-square table. So um, what we really need is these two numbers. So the one on the left, we can look it up on the column heading 975, and then we have 19 degrees of freedom, which I'll write right here. Again, 19 degrees of freedom. So we're going to look them up right now in the table, and then we'll see how Excel can handle this. All right, so let's go to the table. Let's see, where is it? I thought I downloaded this. Let's see. There it is. So the first one we want, the column header is 0.975 right there. And the degrees of freedom is 19 right here. So the intersection between those two is 8.907. So that would be the first of the two critical values. And on the right, what's going to be different this time is the column heading is 0.025, again, combined with 19 degrees of freedom, 32.852. Those are my two critical values. So if we were doing this by hand, this is what we would use in our formula. But since we're using Excel, we're going to use its formulas to get the same numbers. The question is how? Okay, so it's not something you use on a regular basis. The chi-square is a very specialized distribution. So you can find what you need in the slides. They very helpfully, although the picture is really small, I must say, you're going to type chi-square dot inv. And the probability is, when they say probability, they mean alpha over 2. So we're going to type that as D7 over 2. And then degrees of freedom is n minus 1, which means D3 minus 1. All right. Looks familiar. Yes, it does. It's the same one. For the upper tail, though, the command is different because they have a separate command for the right tail of the distribution. So X is, again, alpha over 2, meaning D7 over 2. But the right tail, the degrees of freedom, oh, that hasn't changed. It's D3 minus 1. Oh, now something's not right, obviously. All right, let's try that one more time. chi-square. Oh, I must have typed the wrong thing. inv.rt. I think I typed dist instead of rt. Alpha over 2 and d3 minus 1. There we go. Okay. So now this point estimate means just our sample variance. Okay. So they could have said that, I guess, but um, point estimate, we'll go back to the slides. I don't know what's going on here. The mouse is getting a little peculiar. Um, so lower limit, so point estimate is just D4. Oh, yeah, the mouse is getting a little strange here, but all right. D4, yeah. So in other words, they're just saying it's the sample variance. Now the lower limit, let's go get a copy of this formula out of the slides so we can see what we're doing. There it is. Okay, that didn't work. I probably didn't hit the button hard enough. There it is. Okay. So in other words, you can see on the left, we have the degrees of freedom times the sample variance, all divided by the critical value. Okay. So the lower limit is degrees of freedom. Don't have that listed separately. All right. So we're going to have to do this. D4 minus 1 times the sample variance, which is, well, we can use this. Now we're going to need more parentheses here because there's a operation, algebraic operation in the numerator. And then we can divide by the larger the two critical values to make sure that this ratio is the smallest of the two. And then the difference with the second one is that we divide by the smaller of the two chi-square values. So we need D3 minus 1 times the point estimate divided by the 8.90. 1, 2, 3. That'll work. Okay. So now keep in mind, those are variances. That's why they look that way. If we needed the standard deviations, we would just take the square roots. Okay, but they don't seem to be asking for it. So let's take another look. Yeah, that's it. That's all they wanted. Okay, so you can save this one and you can send it to me if you haven't already. In a second, oh, there's a picture of what the answers were supposed to look like. We're going to move on to the next one, which I think is the school buses. There's two that involve buses. All right. Let's see which one it is. So now we're going to do some hypothesis testing with a single population variance. This is our test statistic, which is surprisingly simple. And Now, you see, now they're going to talk about the p-value approach. They're basically what they're doing here is they're interpolating from the table. We don't need to do that. We can do that in Excel, but when we're using the calculators, I think it's easier to just use the critical value test statistic approach. That's just my opinion. Uh, So it's the St. Louis Bus Company. That's right. They want to know if the drivers are maintaining a consistent schedule, which means they want to know if the variance is too high for being the cutoff point between good and not good. So this is a right tail test. And the data they're giving us is the sample is 24, which I think they expect us to figure it out ourselves. So let's go do that. Not that one, this one. Bus times. Okay. So here you count, and then we have the data is in cells A2 through 25. All right. Once again, let me make that just a little bigger. The sample mean is average in Excel, A2 through A25. And the variance, of course, is var.s. Remember, it's a sample. Again, A2 through A25. All right. Now, the hypothesized value is 4. Okay, that's what we're comparing our results to. The test statistic, again, let me get you a copy of that so we can compare them. And we have n minus 1. Actually, we'll need two parentheses. N minus 1 times the sample variance divided by the hypothesized value. Okay. And that's going to give us our test statistic. Yes, approximately 28.18. The degrees of freedom is n minus 1 for this application. Now, I went over this the other day, I went ahead and calculated the critical values and we did the comparison. Here, they're just asking us to do the p-values instead. And of course, the commands are a little different than what we're used to seeing. Let's see. So the Excel command, and these can be a little bit confusing, but here's what they want us to do. Chi-square dist um, asks for D9, which is the test statistic. Degrees of freedom is D10. Cumulative is 1, which means true. Now, in the slides, they're actually using the word true. It means the same thing. 1 and true are the same. 0 and false are the same. For certain parameters that you enter into these formulas, the variable is a yes or no variable, and that's what this is for. Now, for the upper tail, it's the right tail. So in other words, it's chi-square dist.rt, meaning the right tail. X again is the test statistic. Degrees of freedom is here. .209 something. Actually, let me do this one thing here. If you hit Control tilde, tilde is on next to the 1, you can show all the formulas at once, just in case you missed something. Let me do that right now. That's pretty nice. So Control tilde, tilde is that little squiggly character next to your 1. If you do that, it'll show you all the formulas at once. Then to get out of it, you hit Control tilde again. Okay, so you're just toggling back and forth. All right, and now remember, they love this formula. They do this all the time to us. The two tail, they're just going to do equals 2 times min of these two results. I guess it works, so we'll stick with it. So this is what we're looking for. All right, I'm going to flip it back to see the numbers. Now, no matter which, this is actually meant to be a right tail test. So, but I mean, these p-values are awfully high. Our alpha in this case was 0.05. So that means we do not reject the null. And of course, that means they don't need to do anything about the buses because they're arriving in plenty of time. Okay. So this one is done. You can save it and fire it away to me. The third and final one is just a very quick application of the data analysis tool pack because doing it ourselves would take a while. And I'm not, yes, Excel has the commands to do this, but we're going to stick with the data analysis tool pack today, or for this one, which is school bus. Now here, there's some district that's looking to two different companies to decide which one to hire for their bus service. They want the one with the smaller variance. Just save these. And so therefore, what do we do? All right. So now normally I would have typed up what we need are looking for, but this time, because it's the data analysis toolpack, we don't really have to do anything. So if you look in the slides, you'll see that you're going to very simply, oh, by the way, here's the first time we're seeing the F distribution. The F distribution is constructed as the ratio of two chi-square random variables, each divided by its own degrees of freedom. And so because of that, it looks a lot like the chi-square when you draw it. The complicating factor is that you need two different degrees of freedom, which are known as numerator and denominator. Okay, now we're not going to need the F distribution again for a while. I'm pretty sure it doesn't show up again until chapter 14, maybe 13. But we need to understand it as well. But I don't think Excel has what we need to avoid using tables to look up its values. Okay. So here we have the right tail test. Oh, and that was the other thing too. This one is a little unusual because there's really only two hypothesis tests available to us. We've got the normal two-tailed test. Also, instead of having a left or a right tail, we only have a one-tail test, which is written, as you see here, greater than. And that's because we always choose the variances to make sure that the one on top is larger. So in other words, we have to define the populations in such a way that this ratio is always greater than one. And that's something we haven't seen before. So anyway, let's take a look at the spreadsheet. So they're comparing the performances of the two companies, Millbank and Gulf Park, and they want to test the hypothesis that the variances are equal. If they're not, well, we'll choose the one with the smaller variance. Two-tail test. So we're going to come in here into the data analysis tool pack. And yours could be a little different if you've got a Mac. There's only one in here that refers to the F distribution, so you don't have to think about it. So variable one is here. Oh, what happened? Oh, that's strange. It's refusing to let me select it. All right, you know what? I think I've done something wrong to this spreadsheet. I better get out of it. I'm going to open up a new copy of it. I clearly did something to it that I should not have. Let's get this one open. All right, so I think this is where I went wrong. You see how it always starts out in protected view. If you hit enable editing, you're fine. But I think I accidentally clicked this off, which means it assumed I wanted to stay out of that mode. So, all right, let's try this one more time. Insert, or not insert, sorry, data, data analysis, F2 sample test for variances. There we go. It went to H27. Okay, a B1 through B17. Make sure you choose the labels. I think alpha was different though. Let's go back and double check. Yeah, it's 10. Okay, 10%. Let's change this over here. And we can ask it to put the results in the same spreadsheet rather than a new one by saying, we'll put the output range, tell it the starting point. I'll ask it to put it on D1. Although now these usually you usually have to widen them up a bit. They're giving us the values, the means, the sample means, the sample variances, the sample sizes, degrees of freedom. This is the F statistic. And if you wanted to look it up in an F table, you could find the critical value, but instead, they've given us p-values. And so I think it was 5% here. Let's just confirm. Oh, you know what we have to do? We have to double this. This is one of the confusing things. They're only showing us the one. That to me is a bad idea, but because it's a two-tailed test, we have to double the p-value. So we're going to put 2 times this 04. It's but remember alpha was 0.10. Right. Okay. So therefore, the p-value is less than alpha, and that's fine. We can reject the null, that the two are equal. Okay. Yeah, the null is rejected. So since the p-value is less than alpha, reject the null hypothesis and accept the alternative that the population variances are different. So that's really all that we can do. They have to take it from there. We don't know which one is lower. although we can probably guess because the variance in Gulf Park is quite a bit lower. But as far as the problem goes, they just wanted to know yes or no, are they equal or not? And the answer is no. Okay. All right, so that one is done. So you can save that and hand it in. And then we can start chapter 12, which is all about chi-square this time, right? There's no F just yet. That comes later. Oh, one other thing I wanted to mention too, the first midterm is based on chapters 9 and 10 only. So technically, you should already be ready to do it. Although, you may want to go back and review before you start it because it's set up to only allow one attempt at each question. So you don't want to take it until you're ready, right? Unlike the assignments where you get three, these you only get one, but it's not posted yet, but I'll let you know when it is. So let's go find chapter 12. Here it is. Here it is. So here, there's some more yeah, there's more spreadsheets. Um, we'll see how far we get tonight. We don't have to do spreadsheets every single time we meet, but we don't want to get behind either. Give it a minute to wake up. All right, that's too long. Let's try that again. So anyway, let's see what this is all about. Hmm. All right, so in chapter 12, we're going to look at three new types of tests. They're all hypothesis tests, by the way. Goodness of fit, although the name doesn't sound like a hypothesis test, it is tests of independence and testing the equality of three or more population proportions. All of these are applications. Let me confirm that before I say anything more here. Um, oh no, this one is different. The proportions have their own test statistic. Oh no, I see. No, no, that's right. No, it's done the normal way, but there's an additional step if you want to know which one is different from the others. Okay, but we're not going to see the F distribution in here. All right, now goodness of fit. What is this all about? Well, up to this point, every time we ran a hypothesis test, we're trying to find out if, let's say, the population mean had a certain value or the population proportion. This is a very different type of setting. What we're trying to do is find out, write this in here, with a goodness of fit test, we are trying to find out if our data set follows a specified probability distribution. All right, so this is new, isn't it? Now, I'll tell you when this comes in very, very handy. Many of our statistical tests that we use, although we don't always talk about it in any great detail, um, all of them have some assumptions going on behind the scenes. But one of the more common assumptions is that the data that we're using are normal. Okay, so many statistical procedures are based on the assumption of normality. Well, I mean, how can you tell? I mean, usually what's happening in these problems that we're working on is they tell us that the data are normal and then we carry on from there. But I mean, how can you really be sure? Like, for example, what if you have data and you gather it up into a histogram or even a curve? Like we know the normal distribution is supposed to look like this. But what if our data looks like this? Well, all right. It's hard to tell from those. Those are such awful graphs. Let's do the histograms anyway, just to give you a feel for what we're trying to do here. So we know what the normal looks like. It's symmetrical about the mean. Okay, so imagine this is the normal distribution, and this is our actual data set. Well, it's clearly not identical to the normal distribution, but is it close enough that we can use our procedures anyway without causing any major problems in our accuracy? So it's hard to tell. You know what I mean? So it's just, it looks pretty normal, but is that good enough? So we need a formal procedure that lets us ask, are the data normal or not? Yes or no? And so that's what we're going to do with the goodness of fit test. It isn't necessarily going to be the normal distribution. It could be any distribution. So that's what this is all about. Take our data, compare it to an assumed distribution, and see if the data do follow that distribution or not. Okay. So it follows this test statistic we'll be using follows the chi-square distribution. So let's see what they have for us. So now the null in a case like this would be um, all right, I'm going to trim this down a bit. Our data follow a specified distribution. The alternative is that they do not. It's either yes or no. Okay, either like if you're comparing it to the normal, the null is that the data are normal, the alternative is that they're not. Now, if they're not, it doesn't tell us what they do follow. It just says they don't. Okay, now, so in order to construct our test statistic, what we're going to do is create two data sets. So let's say that we're keep doing something really simple. Let's say that our assumed distribution, oh, let's make it even Crazy simple. Suppose we're running a store, and let's say that we want to compare our assumption to the actual data. So we have two categories of data. During the weekday, we assume that on average, we have 50 customers coming into the store. And on the weekend, we believe that we average 30. Actual distribution from our sample, let's say we choose a sample, we observe the actual numbers for the last 100 days or 100 weeks, whatever. It's 62, and on the weekends, we get so the question is our assumption correct? Is this really what our customer frequencies look like? So these numbers on top are the expected frequencies. Label these E1 and E2. And then these are the um, observed frequencies. In this book, every book is different. It looks like they're going to use E. Some books use O for this. So let me just double check. E, yeah, it's E. Okay. Oh, sorry, it's F. F for actual or observed. All right, I didn't leave myself a whole lot of room there, but these are the observed or actual frequencies. We'll label these F1 and F2 because there's only two of them. And they mention it here in the slides. Observed or actual frequencies for that category. So all the data is organized into categories. Here, the categories are weekday and weekend. Okay, it could be anything. But the assumption they were making, expected, is these up here. We've, we think we understand how the customers are behaving. So this is assumed and this is actual. And we may find out that our assumptions are no longer correct. Okay, so that's why we're doing this. So the test, when you see the test statistic, I hope it'll make more sense. I think they're using the letter K here for categories. Yeah, okay. So you're summing up the squared differences between the Fs, which are observed or actual and expected. Square the difference, add them up. Down here, we're dividing by the expected. That's our test statistic. This test statistic has degrees of freedom, or I should say the critical values will have degrees of freedom equal to k minus 1. K is the number of categories, which in our case is 2. Although it's usually more than that, but still, the one constraint here, and you notice there's always constraints. This is the assumption we're making here. Each category has at least 5 in their expected frequencies. Okay, and we have that. Okay. All right, and then the test statistic. Oh, by the way, I almost forgot to mention, because of the way this is constructed, the test is always conducted as a right-tailed test. Because of the way it's set up, when the null and the alternative hypothesis are yes or no like this, we end up with a right-tailed test. We can't have a two-tailed test or a left-tailed test because it's either they do or they do not follow this distribution. And so therefore, the critical value will always look like this. Alpha, and I'm going to write here k minus 1 degrees of freedom. Okay. So, with all that being said, why don't we do an example? All right, here we go. So we have a market share study conducted by Scott Marketing Research has identified that this market share for product X is shared by 3 companies, ABC, and the company C has a new product they want to bring out, and they want Scott Marketing to find out if the new product will alter the market shares. Okay, so um, I think, yeah, let's do it let's follow their lead here. The companies are A, B, and C. And these are the expected frequencies. This is what they currently have. Okay. So they're telling us that the probabilities of being in each category are 30, 20, 50, and 20 respectively. Uh, and they know that from historical experience. In other words, they're saying that this market share, actually, I should have put this in here first. So it was, once again, 30, 50, and 20. and the sample size is 200. So in that sample, the expected frequency based on historical experience will be, so you're just multiplying those proportions or probabilities by 200. That will be defined as E1. Oh, sorry, that's 40. What am I doing? Now, some problems they'll just give you the expected frequencies. Here they're telling you how to calculate them. It's a simple matter of multiplying the proportions by the sample size. So, based on our historical experience, this is what we'd expect to see in a sample of 200 customers. Then they have to give us the new ones. In other words, they actually go out and do the research and say, well, how many people now are buying the product from these companies after the introduction of the new product? So, if the same three companies, and then here we have what are called the observed, which are the actual frequencies. And they have to be given to us in here somewhere. Um, there we are, 48, 98, and 51. Yeah, they do. Okay, so this is F1 for observed frequency, F2 and F3. All right, so finally we can calculate the test statistic. So the null, by the way, an alternative would have been, I guess we could express this in a few different ways. But what they're getting at is the proportions have changed or they haven't changed. So where the null would be that they have not changed after the release of the new product. And they were, once again, 30, 50, 20. The alternative is that they are not. All right. So now the alpha is 0.05, I believe. We don't want to get spoiled the surprise. Yes, 0.05. Test statistic, again. This time there's three categories, by the way. So we'll have, so now we just plug in the numbers. Let me go get them from up here. So let's see, where are we? We've got 48 minus 60. And we have in the second category for company B, we have 98, 100. And then finally, we have 51 minus 40 squared over 40. All right, let's figure that out. So this one is 144 over 60. Wow, a lot of fractions. So I'm going to round them all. Oh, this one, first one is 2.4. Oh, I goofed. Sorry. I just noticed it. Sorry, this is not 9, it's 11. 11 squared is 121. Yes, that's better. 3.025. Now we'll add them up. I got 5.465. Let's see what they got. Once in a while, the typos do show up in here. First one is 2.4. The second one is um oh, wait a minute. Yeah, there's two typos in there. This one is 98 minus 100. That's still 4 over 100. But this last one, 11 squared over 40. Yeah, that's 3.025. Now they goofed. It's not 7.3. It's this number here. And now what about the critical value? Now remember, the critical value is all in the right tail. And the degrees of freedom here is k minus 1. So I think they asked us for 0.05. Yes. So go to our chi-square table, look for the column headed 0.05 with 2 degrees of freedom. Yeah, I don't know why. Oh, here it is. That's why. So remember, it's 5% right tail, 2 degrees of freedom, which puts us right here, 5.991. This is the rejection region. Test statistic is 5.465, which means we're not in the rejection region. So we do not reject the null. Um, the proportions, therefore, do not change. Okay. So that's your classic chi-square test, a goodness of fit test, rather. The only thing that changes from one to the next is the actual data you're given, but the process is the same. Now, again, because of the limitations in the calculator, we're not going to do the p-value, except in Excel. Okay. Now, I am going to show you a special trick, though, with this data. Now, here we only have 3 categories. The test statistic wasn't that difficult to calculate. But what if we had like 10 categories? It could get to be quite a headache, and there's chances of making a typo are quite significant. So I think you'll be pleased by this. Now, what I'm going to need to do here is write these out a little better. So here we have 48, 98, 51. Here the expected frequencies were 60, 140. And the test statistic, remember, so here's what we're going to do. We're going to enter these data into lists. Now, we did this somewhere, I believe, in the early days. So let's remind ourselves how to do that. I'm going to do this. Stat, enter. You're already where you need to be. Just hit enter. And you're in the lists. Now, what you're going to do is put the observed frequencies in list one. Um, and in L2, you're going to put the the expected frequencies, observed and expected. If old data is there, you can clear it out. What you have to do is go to the top, go to the header, not the first row of data, but go to the header with your arrow key, and then hit the clear button, which is over in the far right. That will erase the entire column. So do that first, and then type the numbers. And then for L3, we're going to do something pretty amazing. What are they? 48 and 60. 98 and 100. Finally, 51 and 40. Do that first and prepare to be amazed by what this thing is capable of. So we're going to go to the top of L3, the header that is. You're going to type open parentheses, second one minus second two close squared divided by second two, which is the same thing as saying, so in other words, yeah, so in other words, list one is F, list two is E. So instead of F and E, we have list one and list two. So it's the same thing. Then you'll see it will fill itself in automatically. The three values that show up are 2.4, 0.04, and 3.025, which we figured out already. And now you can either add them up manually or else, if there's a lot of data there, you can ask the calculator to do that for you in the following way. Let me just put this in here to remind you what we just did. So to add up column L3, go to Stat, Calc, 1, our stats, enter the list, tell it you're interested in L3. This means type second comma, not second comma, second three, because this is equivalent to L3. All right, so if you notice, if you look at the keys, the second function of 1 through 9, they're all lists. Once you've done that, go down to calculate. You can skip over a frequency list. And the number you'll want is the one that's labeled sum x. Yes, and this is the one that we got manually by hand. That is your statistic. Oh my God. Now, with three observations, it may not be worth all this trouble to go through, but if you've got like five, six, seven, eight columns of data or categories, it starts to become a nuisance to do this test statistic. And so knowing how to do techniques like this could potentially be enormously time saving. Okay. I'm not saying you have to do this, but it's good to know that it's there if you need it. Okay. So this is, like I said, your classical goodness of fit test. You can use it for any situation. As long as you've got expected and observed frequencies, you are all set. Oh my God. And so, like I said, often the biggest application of it is to compare your data with the normal distribution, but you can use it for anything. All right, now what else do they have here? I'm not sure if just get this in here. See, now they're using the wrong numbers. I mean, we got the right test statistic and the right critical value. They've unfortunately got the typo in there that ruined the whole thing. Now, there is an Excel spreadsheet for this, and we will do it, but maybe just not right now. Um, okay, so we're moving on to the next one. Tests of independence. What is this all about? All right, well, imagine the following situation. Another application of the chi-square, by the way. So you've got a company, with whatever product they sell, they have to understand their demographics, the market that they're facing. And so suppose that a corporation wants to know, well, let's make it more specific than that. Starbucks wants to know if men and women like the same flavors. Um, in other words, if I made up a chart of the favorite flavors for the whole company, would the proportions be the same among men and women? Okay, that would be a test of independence. If they find that there's a connection between the two, then they might find other ways of marketing their products. They might say, well, maybe if the women like this flavor better and the men like this flavor, we should promote it in different ways than we're doing now. So this would be what we mean by a test of independence, or maybe movie theaters. Now, you know that movie theaters often have lower ticket prices for seniors. Why do they do this? Okay, you'd think they'd be losing money, but the reality is they're offering a lower price to seniors because seniors tend to be more price sensitive because many of them are on fixed incomes and they can't afford, to spend a lot of money in movies. If we find out though that seniors and non-seniors prefer the same I mean, if it doesn't make any difference to them whether you give them a discount, then maybe we should stop giving them a discount. So, and, you're trying to promote your product to whatever demographic is interested in it. So it's very important to know if in what ways that your customers are different, they perceive your products differently. Okay. What if men and women like the exact same Starbucks flavors? Well, then you're not going to advertise differently to the two groups. What other possibilities? There's so many possibilities, but when they say independence, they mean independence of characteristics. Okay, not the populations themselves, but the characteristics of the populations. So, how do we test such a thing? Well, we start out with the null and alternative hypotheses. The null will be that the variables are independent. In this case, it would be gender, male, men and women. Oops. And the alternative is that they're not. Okay. And you notice, just like with the goodness of fit, it's a yes or no situation. Either they're independent or they're not. So that means this will be conducted as a right-tailed test. So in other words, there's only going to be one critical value to choose from. Now, unfortunately, this setting this up is a little bit messier than goodness of fit. There's more going on. So the test statistic will be a little bit messier. Okay, it can't really be helped, but we'll survive. Don't worry. This is also when we may want to consider using the calculators again. So here's what we have to do. We have, well, what do you know? Doesn't this look just like the other one? But you notice there's two subscripts. So F still means observed frequency, E still means expected frequency, but before we were only looking at either one row or column of data. Now we need both. So that's why there's two subscripts. One is for the row in our data table, and one is for the column. So yeah, when we do a problem, you'll see exactly what I mean. Let's copy this, but you can see other than that, it's the same setup. Challenge is really in the calculating the test statistic. It can get very complicated. All right. So, by the way, when all this is done, I'm going to show you another secret. So, something that will speed this up. But first, we're going to learn it the proper way, and then I'll show you the shortcut. Okay. Yes, you have to wait. The shortcut has to wait till after we know how to do this. So, the one other difference, now again, we're assuming that we're setting up our data in rows and columns. So R is the number of rows in our data. C is the number of columns, not including the headers, of course. So the degrees of freedom is R minus 1 times C minus 1. So the test statistic will be written like this. Yeah, remember, it's only right tail, therefore alpha must be the only, this is the only case we have. There we go. All right. So, sorry, I wrote the wrong thing. Sorry, that's the critical value. Whoops. What am I saying? The test statistic is this one. That's the critical value that I just drew. Hold on. And there's only the one. What do you know? This is not very different than the example I just came up with, except that it's beer. All right. So beer, we've got the three styles, light, regular, and dark. And we have men and women, and they want to know if the beer preferences are the same among the men and the women. Okay. It's an important detail for marketing purposes. So the null will be that the beer preference is independent of gender, meaning they both like the same flavors. And the alternative is that they do not. Okay. So here would clearly be not of gender. Okay, so it's got that straight. Now let's copy the data. What happened there? I must not have hit it hard enough. Hold on. Oh, I almost forgot. Hold on. For something like this, you don't want to just do paste. It's going to look awful. We want to paste special, use picture. That's more like it. Let me see, I can adjust it and it looks beautiful. All right, now keep in mind, these are the actual, wait a minute, hold on a second. Let me confirm that. This is the sample. So these are the observed frequencies. These are the Fs. Now here you can see why the Fs have to have two subscripts. So keep in mind that when you write these subscripts, this is the row and this is the column. So that's why like 1 1, 1 2, 2 1, 2 2, 2 3, 3 2. Oh, sorry, this is not right. This one should have been 3 1. Yeah, that would help. Okay. Much better. Okay. So that remember, these are the observed frequencies. What about the expected? Now that's a little bit different because instead of giving you a distribution, what they're going to tell you is that we're looking for independence. That implies that the proportions of men and women have to be the same in each category. In other words, if 22% of the men like the best, then 22% of the women should also like light beer than the best. 50% like the dark, men, women, 50%, and all the way down. So we don't need an actual distribution. We can figure it out directly from these numbers. In other words, we can calculate another table in which we say if the two genders are independent of each other, what kind of totals would we expect to see? Meaning the proportions are the same in each category. That's what we're going to do next. That's where all the time goes, by the way. Well, actually, I shouldn't say that. The test statistic is also pretty time consuming. So they're going to show us how to do that next. Oh my God, look at this table. You know what? I just realized they didn't. That's how they did it. Because I copied the wrong table. These are the observed, these are the expected. All right. Well, I'll tell you what. It's time to show you the shortcut. Rather than reproducing this horrible table, what I'd like to do is show you the shortcut right now, okay? There's no point in fooling around with this. Um, take the actual data right here. Let's make sure we got this straight. Um, so that means that this table is not correct. It's this one. I got it wrong. I'd still be able to say that. There you go. Okay. So let's confirm that one more time. These are the observed, right? Okay, great. So I'm going to show you the shortcut now to avoid all of this dreadful calculation. And when you see it, you're going to say, this is absurdly easy. I am so glad I bought this calculator. But you have to know how to do this. So in order to construct the test statistic, but it's a lot of work. Instead, we're going to do this. So you're going to go to the calculator and hit second, and you'll notice there's a button over in the far left labeled X inverse. Directly above it, it says matrix. So when you hit that, what you're going to do is scroll over to edit. You're currently at A, by the way. Scroll over to edit, enter, and you'll see that it says matrix A, 1 by 1. Those are the dimensions of the matrix. Rows, columns. It's not what we want. The data we have has 3 rows and 2 columns. Don't count the totals. These numbers here, that represents a matrix with 3 rows and 2 columns. If you type 3 and scroll over, you don't need to type the X. Um, and you'll see a 3 by 2 matrix where we enter these numbers. Well, this will only take a few minutes. So in other words, you 56, 25. So go ahead and type those in. Um, you'll notice that as you're going along, you need to move around the cells with your arrow keys. You also have to hit enter after each one. D1, 56, 25, 30. Yeah, that's it. So now what? All right. Go now to stat. Actually, I'll tell you what, before we do that, let's go back to matrix. Second inverse, X inverse. Scroll down to B. Oh, actually, I'm sorry. It won't be ready yet. No, sorry. I take that back. We'll get to this in a minute. Instead, do what I was about to do. Stat tests. And the one you want is letter C, I squared test. Now, if it says there in your calculator, which it should, observed A, expected B, leave it like that. That's what we want. Okay. Although technically it doesn't really matter which letters you're using, I guess, as long as it knows that your data you just typed is in A. Okay. The B, the expected could be any letter, but ideally it should be A and B. And you go down to calculate. Now, what is going on here? This is what comes out of the calculator. And this is your test statistic. This is clearly your p-value. And of course, this is your degrees of freedom, which you would need to look up your critical value if you use it. But we don't need to because we have the p-value. So if you look in the slides, let's see, they're going to tell us that Yeah, they're agreeing with our test statistics, 6.446, 6.45. And this was done with a 5% alpha. And so that means p value is less than or equal to alpha. We reject the null of independence and accept the alternative that they're not independent. Okay. So in other words, it means that men and women like different flavors of beer. Now, had you decided to look up the critical value, this is what you would have needed to do. Got chi-squared, and remember, it's alpha, and degrees of freedom is r minus 1, c minus 1. So therefore, you need r, remember, was 3, 2 times 1, which is just 2. Go to the table and look this up. 5% in the right tail combined with 2 degrees of freedom. Actually, we've seen that one before. Look, there it is, 5.991. And so, of course, that means that our rejection region is anything to the right of that. Remember, we did say this is a right-tailed test. But since we found our test statistic to be 6.446, that, of course, puts us in the rejection region. So therefore, of course, we reject the null. In independence between gender and beer flavors. And of course, accept the alternative that they're not. Okay. Right. Okay. So we already figured this out with the p-value. Now we've shown it with the critical value in the test statistic. But there's an added bonus here. If we go back and revisit matrix B, this was A. Let's see what's in there. Um, 59.4. Now I'm going to do this for a reason. You'll see. If you look in the slides, you'll see pretty quickly what these represent. Ah, here we go. Although it's set up differently, those are the expected frequencies. These are the observed frequencies that we were given. In other words, the Fs. These are the expected. In other words, these are the numbers you would get if preferences were literally identical between men and women. So the test statistic was calculated by comparing all these values cell by cell. So you can see it saved us an awful, awful lot of time. These are IJ, by the way, because it's rows and columns. And that was enough reason to buy this calculator. I think you'll agree. Just that by itself would be enough. We've gotten so much use out of it, but oh my God, it just never stops giving, does it? All right. And so you can see the similarities between test for independence and goodness of fit. It's just that with independence, we're specifically looking for the distribution of independence, whereas with the goodness of fit, we can use any distribution. Okay, well, whew. What else is there in this chapter? Oh, here it is. Oh my God. The equality of proportions, three or more. So this one actually is surprisingly similar to the test of independence. In fact, you can see it's the same test statistic. So you know what that means. We're going to use the same technique we just did, putting the data, observed frequencies into our matrix and then running it from there. And again, later on, we will do these in Excel. We'll probably look into this. I don't know how important this part really is. Um, where after the fact, if you find that the proportions are different, to try to figure out which ones are different. I'm not sure if they're going to ask about this in MindTap or not, but we'll see. Oh, all right. So what's happening here? Got three proportions. So remember, this book uses P as a population proportion. P with a little bar over it means sample proportion. Okay, so testing hypotheses. All right, so we got three. It's actually three or more. All right, we'll stick with three for now. So here they're all equal. Now, if they're not all equal, there's a lot of other possibilities. So we're going to lump it all together by saying not all are equal. You could have like one is equal to two, but not three. Three is equal to two. There's so many possibilities. And of course, we choose the alpha. The test statistic looks very familiar. For the example here, I think they want 0.05. Where is it? Let's just use 0.05. And of course, the test statistic is just like before, double sum, one for the rows and one for the columns. We're not going to actually do that ourselves, are we? We're going to let the calculator help us. So what data? All right, here we go. Um, this is coming from here. Okay. So the proportion that we're talking about is proportion we're likely to buy that car again. So the data that goes into our matrix is right here. So let's go back to matrix A. We have to change the dimensions, by the way, because this one is 2 by 3. Two rows, three columns. And then we're going to enter these numbers, okay? All right, let's try that. So you have to edit, hit the edit for A, change the numbers to 2 by 3 so you can put all the data in properly. You can type over the existing numbers. All right, when you're done with all that, um, is go to the chi-square test once again. So enter the data, then do stat tests. Scroll down to C, chi-square test. And again, observed, expected, leave it at A and B. And then calculate the color. They're asking about the color. I'm not sure why that shows up here, but I'm not going to touch mine. Uh-oh, I did something wrong. Oh, you know what it is? Okay, I believe what it's upset about is that we have to go back and change the dimensions of B as well. If that doesn't work, then I'm not quite sure what the problem is. So go back to the matrix mode. Change B to 2 by 3, please. If that's what's upsetting it, I would expect it to figure that out for itself, but maybe not. No, it's still giving me a hard time. What's going on here? No, that can't, there shouldn't be any problem with this thing. Something's, I don't know, maybe it's just my calculator. It's not working. It's refusing to let me do it. It's very strange. I've never seen that before. The exact same setup as the last one, except the dimensions are different. This is very frustrating because this is a very complicated problem, and I do not want to do this by hand. I don't know what the problem is. Well, I'll have to look into this. I really don't know why it's objecting all of a sudden. It's the exact same setup. I mean, if we're really pushed to the wall, we can put this into lists. But I mean, it's so ludicrous that it would refuse to work on one example over the other. Very annoying. But you know how technology, like I say this all the time, always lets us down. Same calculations for the expected frequencies as well. This is what it was doing before. All right. Well, anyway, I guess, we've been doing this long enough. Why don't we stop right here? We'll work on this tomorrow. We'll start this from the beginning. If we can't get the matrix to work, we'll just do the lists because you don't want to do this by hand. And then when we're done with this, we can go back and visit all the Excel spreadsheets in here. And it's very straightforward in Excel, as you can probably guess. So, all right, I guess we're kind of have to stop right here. I'll try to figure out what's wrong with the calculator, and if not, we'll just use the lists. Okay. So, all right, I guess we'll see you tomorrow night. Now, remember too, I did send out a list in advance. All the links for the whole week are in the email that I sent you on Sunday because I knew there was a chance I'd forget about it during the week. So if you don't hear anything from me, just go ahead and sign in with that link. Okay. Because there's a very real chance that I'll forget all about it. I'll open up the computer and nobody's there. So it's in your Sunday email. Okay. I'll try to send it to you tomorrow, but if I forget, just log in anyway. All right. So I guess that'll be it, and I'll see you all tomorrow.
Thank you.
All right. You're
Thank you.
welcome. All right. Good night. Good night. Oh, I have a chat. All right. I hope you haven't been waiting too long. Yes, go ahead. Yes. No, I can't hear you, but I can read your message. Oh, what is that? Actually, you know what? Let's tell you, we don't want everyone to see what we're talking about here. I'm gonna uh oh, does it really, is it in there? It says I didn't your Blackboard says 0 for 10? No, 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 no. I don't know where that is. Where could that be? Well, I didn't put it there, let me tell you. Um, submit it. Oh, if you found a link, oh no, no, no. We use this during the spring. We were using links for the Excel instead of email. Um, no, no, I'm not using that system right now. Don't even just completely ignore it. All I'm doing is looking at the ones that are in my inbox. If it says 0 out of 10, just ignore it. It doesn't mean anything. I didn't realize that was there. Um, and certainly I didn't know. Let me go look in Blackboard. I thought I got rid of everything from the spring, but I must have overlooked something.
Hello?
So I don't right. There's something wrong with your computer. So I'll type it here.
Don't worry, I got it fixed. Anyway, so you were saying?
Oh, yeah, I don't know what you're seeing in there, but it doesn't belong there. It might be
Got it.
something left over from this. Well, it
Okay.
wouldn't even be last spring. I didn't teach this class last spring. If you saw something in there that said 0 out of 10, just ignore it because that's not right. And I don't know where it came from or how it got there.
Got
But
it.
don't even worry about it. Okay.
Got it, of course. Because I was just looking through everything and then because I emailed you the stuff and then I just see a
Yeah.
0 out of 10.
No. There should not be anything in there that says anything about Excel. I did
Okay.
not choose it. I definitely did not tell it to do that. So
Of
I'll
course.
see if I can delete it. Okay.
Hmm. Okay, no
But
worries.
just forget it doesn't exist. Okay.
Yes, got it, got it. Thank you so much. Have a good rest of your day.
All right.